check mark mean that we're gonna do a fresh versus process?
What?
Sorry. I said, does the check mark mean that we're gonna do a fresh versus process DVD?
No, that always means like, I like this.
I mean, I feel like we should.
Yeah, I feel like we might have to in the future.
Just to like prove some sort of arbitrary point that nobody cares about a subject. Sorry.
Oh, I'm in a Zoom meeting, but it's not that important. And I'm gonna have to leave anyways for class. But I'm just attending because I guess I'm here. Okay, bye. Yeah. Try to, let's see about coffee.
Next term, there's a class at one that I want to take, but it's during our like recession. If I miss our recession, do you think I will pass the class? Or should I just?
Well, recitation, I mean, we usually just do the quizzes during recitation. I guess, like, worst case, I could send your quizzes to the testing center or something, or you could do them during lab. So I think we could make it work.
Okay, thank you.
Yeah.
right, let's go ahead and get started. So I hope everyone enjoyed their snow day. I did. All right, so now we got to power through chapter 19, basically. But of course, ask questions. We can always continue chapter 19 into next week if we need to. And so kind of, are there any questions before we get started, by the way? Yeah.
Did Enoch play in the snow?
He did, yeah. I took my little baby outside, yeah, and he played in the snow. Any other questions before we get started?
I did not watch her baby from afar. The snow, I watched from afar.
Can we do a lab next week?
That's so creepy.
Yes, oh, let me go over that. So labs. So obviously the Tuesday lab, you kind of got shafted. And so Thursday, we'll have our regular lab today. And if you want to join us from the Tuesday section, you can. So today is going to be an equilibrium lab. And then, so this kind of means, and this maybe works out in your favor. So next week I was planning on doing kind of lab final / checkout, but there's not going to be enough time for the Tuesday people. So probably next week will be like a short paper final. And it'll be weighted like the same amount as like a lab report. I expect it to be like 10 questions, multiple choice, and then probably a checkout portion. So we can clean up a little, find out who the hoarders were. And then on Tuesday, we'll make up, of course, the regular lab as well. So regular equilibrium lab. And then don't forget about your papers. So I think I went through everybody's paper, check-in, turn-in. They look good. I like the topics. And then if you need help, just let me know. Like I would craft an outline too before you get started. Some of you have like big topics, so don't be afraid to kind of like chop it down and focus on a small portion to get like a succinct paper. But otherwise, I really like what I'm seeing. All right, so let's dive in. And again, as always, ask questions, stop me. And so we've been studying how fast reaction rates go. And so now we're going to study how far the reaction goes. And so just a quick recap. So we're going to get into this sort of equilibrium arrow. So when you see these two these two half arrows, this signifies that we have some sort of equilibrium. So we can go right forwards and backwards and forwards. Versus, so we've talked about resonance before. So if you have a double bond, I'm trying to think of a good, or this is a better example, sorry. So when you have something like this, then you can draw that arrow with an arrow on each end and show resonance. So that's where you just move your electrons around. So just keep that in mind. So now we're going to be seeing a lot of equilibrium arrows in this chapter. Again, don't get it confused with the resonance arrows or anything else. So I'm going to skip this journal article, but you can read it at your own leisure and see how they measured this constant. So doing studies, but basically let's look at an overview of this. And so hemoglobin is a protein that's found in red blood cells that of course binds with oxygen. And so how it works is kind of an equilibrium. So this is going to be in the lungs. We have a high concentration of O2, and so that means if we have a high concentration of oxygen, it's going to shift to the right to make a lot of our product, which means we have bound hemoglobin plus oxygen. Then your hemoglobin plus oxygen starts floating around your body, then it gets to the muscles, and this O2 concentration is of course low in your muscles after you've been moving around and using up that oxygen. And so that means that the equilibrium is going to shift to the left, so there's a small amount of oxygen. That means this is going to release the oxygen, so the hemoglobin releases your oxygen in your muscles. And then, of course, that hemoglobin goes back to the lungs, where there's, again, a high concentration, and reforms. And so part of what the article is the fetal hemoglobin. So then the next question is, well, how does a baby inside a pregnant mom, how does it get oxygen? And so how that works is the fetal hemoglobin equilibrium constant is larger than the adult. And so that means, right, oxygen, hemoglobin is floating around to the baby. And since that fetal hemoglobin is more efficient at binding oxygen, then it can still bind O2. So the hemoglobin is released from your regular hemoglobin and then released because it's at a higher binding constant. That means that adult hemoglobin releases, the fetal one binds, and is able then to get oxygen. So then oxygen is transferred from the fetal hemoglobin from the mother's hemoglobin in the placenta. And so all that's just a little difference of equilibrium constants in your fetal hemoglobin versus your regular hemoglobin. And so now we'll be looking at our reactions and again how they progress. And of course when a reaction starts, usually you start with a set of reactants, and so those reactants are consumed and products are made. And so we've kind of looked at this with the rate. So the reactant concentrations decrease, product concentrations increase. So again, seeing that in our reaction rate. And then as reactant concentration decreases, that means the forward reaction rate decreases. So we've seen that also with our constant. So it's dependent on something, A to whatever order. So of course, as that decreases, obviously the reaction rate decreases. And eventually the products can react to reform some of the reactants. So again, if we have some sort of equilibrium, now they can go back and forth. And this also assumes that the products are not allowed to escape. And so this usually means that this is a way to drive the reaction forward. I may have mentioned that in here with the Dean-Stark reaction, or this apparatus. And so this takes away water, essentially. And so that could be a way to continue to drive a reaction forward. So if you have some reaction that forms water, you can have a Dean-Stark, so that allows your product to escape and continue to go forward. If products are not allowed to escape, then maybe the reaction will stall out or start reforming, so that sort of thing. So that's where your reaction technique also comes into play. And so as product concentration increases, then the reverse reaction rate increases. And so that makes sense from our rate. So we have B, and so we have the K -1, B in our reverse direction, so of course more B, now more in the reverse direction. And so again, we're looking at these reversible processes right now. So processes that proceed in both the forward and reverse direction are said to be reversible. And so just to compare with, again, all the previous reactions we've looked at, we've kind of looked at the single-headed arrow, so just assuming all reactants convert to products. But now we'll be looking at cases where that's not the case. And so now we have this condition called dynamic equilibrium. And so this is just where the rates of the forward and reverse reaction rates are equal. And so that means that you have no overall change. And so once our chemical reaction reaches equilibrium, the concentrations of all the chemicals remain constant because they're being consumed and made at the same rate. So it looks like nothing's going on, but of course if we zoom in at the molecular level, right, there's still a lot of action going back and forth as they're going back and forth between, in this case, H2 and forming HI, and there's iodine concentration. So still, you still have reactions, so that's still going on. So this is hydrogen plus iodine gives you HI. So still going on, bonds are still being broken and formed with dynamic equilibrium. Again, there's just no overall change. And so this is also a key point. So at equilibrium, this does not mean that there are equal amounts of reactants and products. So they're staying at the same concentration, but they can be completely different. We don't know. We have to figure that out from our constant. And again, the rates of the forward and reverse reactions are equal, but not the concentrations. And of course, some reactions only reach equilibrium only after almost all the reactant molecules are consumed. And the reverse could also be true, so some reactions reach equilibrium when only a small amount has been consumed. So now let's look at, well, what is our equilibrium constant? How do we write it? And how will that help us? So this is your generic equilibrium kind of formula. So notice you have this A plus B gives you C and D, and then we have our little subscripts, our coefficients. So we have our coefficients at the front, and so whatever your balanced equation is, that determines what power we write our concentrations to. So in this generic form, so let's just zoom in a little closer. So notice it's products over reactants, and so I'll just rewrite what they wrote. But all you do, so you take the concentration of C, it'll be to the power of whatever C is, again from your balanced equation. Multiply that times the concentration of D, again raised to the power of whatever coefficient for your balanced equation. And then over reactants, so that's concentration of A to the power of A times concentration of B to the power of B. So I'd write that somewhere. So this is your generic form to give you your K. And so K is just our equilibrium constant, and it is unitless, since everything cancels out with the concentration. All right, so take a minute or two and just so write out what would be the equilibrium constant expression for this reaction. And so you should have written something that looked like this expression. So again, it's just products over reactants. So notice NO2 is raised to the fourth power from our balance equation. So 4 nitrogens, 10 oxygens, so 8 plus 2, so 10 oxygens. Then oxygen has a coefficient of 1, and then over our reactants, so over dinitrogen pentaoxide squared. So everybody wrote that down? Simple enough. All right, let's do another one. Just practice. So express the equilibrium constant for the combustion of propane as shown by the balanced chemical equation. So they gave you a balanced chemical equation. So again, take another minute or two. What would the expression be? So I'll give everyone a few more minutes and then we'll take a poll. So who votes A? B? Oh, looks like everybody likes B. And then any takers for C or D? So excellent job. So it looks like everybody picked B, and that is correct. So if you just wrote it out, so products over reactants. And of course, everything was taken to the appropriate power in B, so everything raised to its coefficients. Excellent. And so now, well, what does this K value even mean? And what can we kind of gather from this? So what does the value of K imply when its value is greater than 1? And so I would just simplify this. So just think, okay, we have products over reactants. So what is that telling us if our K value is much greater than 1? Yeah, one.
We have a lot more particles of products than reactants.
Exactly. So it's favoring our products then from our K. And so the example they give is this hydrogen plus bromine gives you HBr. And so apparently this is a large number. They give it to you as 1.9 times 10 to the 19th. So obviously much, much greater than 1. And exactly, so it's going to favor the products. Very good. And then if we see it now in the reverse case, so what happens if it's much, much smaller than 1? Again, just think simply products over reactants. So now what is this K value telling us? So opposite, so favors the reactants, in case you couldn't hear. And so in this case, we're looking at nitrogen plus oxygen gives you nitrous oxide. And that has a very small K value, so 4.1 times 10 to the negative 31. So yes, it favors N2 and O2, and that makes sense, right? If this was a large number, then we wouldn't have much oxygen left to breathe. So. Questions on that? All right, so now let's do a little multiple choice. So which of the following statements is false? So I'll give everyone a couple of minutes for this one. We'll take a vote. So let's take a vote. So anybody think A is false? So A seems to be true. So K is much, much greater than 1. Forward reaction is favored. Okay, that sounds good. And essentially goes to completion. What about B? Is that false? No votes for false. So same thing. K is less than 1. Reverse reaction is favored. Okay, that sounds good. Forward reaction does not proceed. Okay. When K is about 1, neither the forward or reverse reaction is strongly favored, and about the same amount of reactants and products exist. So no one's moving for that one. What about D here? K is much, much greater than 1, implies that the reaction is very fast. Any votes for D? 1 vote for D, 2 votes for D, 3 votes. Pretty shy. But yes, it is indeed D. And so this is where we keep kind of these chapters separate, right? So last chapter we were talking about reaction rates, but now this K, that doesn't tell us anything about how fast it's going. It's just telling us where and how much product we're going to end up with at equilibrium. But we don't know anything about the rate, even though the K is much, much greater than 1. It could be very slow and, eventually get there even in a couple of years, So we don't know. Right, questions on this one? And so again, we can't say anything about the rate based off of K, so we have to have data for the rate and for the equilibrium constant. Now for some more fun stuff. And so now we can also write relationships between K and our chemical equations. And so this helps us kind of manipulate things and find the rate. And so when the reaction is written in reverse, then the equilibrium constant is inverted. And so that's fairly straightforward. So we have K, let's just call this KF in the forward direction. So of course, products over reactants. And then if we reverse this same expression, now products over reactants. So these are just inverted. And so now we can say, right, our KF is equal to 1 over the K in reverse. So that could help us. So again, all we have to do is, if we know the forward equilibrium constant, do 1 over that, and that gives you your reverse direction. So if you have coefficients for an equation, if they're multiplied, then the equilibrium constant is also raised to that factor. So for example, let's say we're just looking at A plus B gives you C here. And so it's written in its expression for K1. Now if you doubled everything, that would be the same as going, so C to the C. Oops. So if you double everything, then that's just squaring your whole reaction essentially. So you get this, so then you rewrite it, so then K2 is carbon times 2S, or C I mean, A to the 2A and B to the 2B. So K1 is just equal to K2 to your N power. So again, whatever you multiply it by, it could also be a half factor. And so when we add equations to get a new equilibrium, the equilibrium constant of the new equation is the product of the equilibrium constant of the old equations. And so this could be helpful. Let's say we're trying to figure out some reaction. So notice what's going on. So you have A gives you B, and then B goes on to make C. And so let's say you're trying to figure out the equilibrium constant of C, or this reaction. So the overall reactions, of course, you add them together. The B's cancel, and that leaves you with this reaction. And so if we don't know the reaction rate, we can determine it. And so they go through the derivation so you can see how those B's cancel. And so your final rate is just going to be K1 times K2 to give you K3. So you probably need this one at some point too. All right, so let's try to put that into practice now. So I'll give everyone a few minutes. So ask your neighbors too, ask your friend. So we are given our equilibrium constant for our Haber-Bosch process. So N2 plus hydrogen gives us ammonia. And so that has an equilibrium constant of 5.6 times 10 to the fifth. And so what happens if we look at the reverse reaction? And it looks like they halved it as well. So give everyone a few minutes for that. So what are some thoughts? What should we do to this K? Yeah.
I disregarded the fact that they have the reactants and the products because it's going to be the same ratio. We just have to invert it.
So you're saying invert this K?
Yes.
All right, so let's start there. So there we had, basically I'm going to write it out. So we flipped our equation. That means we have our K to the -1 power. We could even rewrite that, what that looks like. So we just flipped it. Then we're here essentially. And then does this match this equation though for K prime? So what do we need to do to our equation and then therefore our equilibrium constant? Both, yeah. So we take our coefficient by 1/2 And so I'll just rewrite it so we can all see explicitly what's going on. And so, oh, yes, so now that gives us the equation we're looking for. And so, yes, you were correct in stating if we take it by a half, then we have to multiply it, our k, by a factor of 1/2, or take it to the square root. So same thing. And so now let's get an actual number. So 5.6 times 10 to the 5th. So I'm going to invert it. And then I could have done the square root, but. And so I get 0.001336 for the new k. So other people got. Other questions on this?
All you did was take the inverse and put it 1/2.
Yep. And you could have also plugged it in with the square root, so. So let's take it to 1/2. You could also do like 1/. I'm just showing different ways to enter it. So you could have done 1/. That number. So that gives you the same thing whether you take it to the -1 power or you just invert it 1/. And then let's take the square root this time since they mean the same thing. So either way you punch it in, you should still get this answer. And so that's our K prime equilibrium constant value. So other questions about this before we at least move on for the time being? All right, let's try another one. So now predict the equilibrium constant for the first reaction given the equilibrium constants for the third and second reactions. So let's at least talk through this. So first of all, how can we manipulate these last two equations to get to this first one here. We might have to do some flipping or multiplying. Not sure what we have to do. Any thoughts? So always identify, like we have methanol here. So where else is our methanol? So at the bottom. So let's just start, I'm just going to rewrite this bottom equation for a second. So that's at least a good start. And I'll just put K3. We haven't manipulated it in any way. And then, so what about the second equation? So what do you notice about this? I'm seeing like it has an H2, but on the product side. So what could we do? So I don't know if we want them to cancel, but we would want to add them maybe, because we have 3, and we have 2 and another one. So how could we add them? So could we flip this second equation maybe? So let's do that, and then let's see where we're at. So flip, and so now I'm just going to write it over flip. So that's H2 plus CO2 gives us CO plus water. And so I'm just going to do K2 to the -1. And that just reminds me that, okay, we flipped it from K2. And then let's pause and see, does this give us what we're looking for? And let's see, so the COs cancel, H2, so this gives us 3H2 plus CO2 gives us water plus methanol. So now it looks like if I add these, again with the K3 and then K2 flipped, I think we get K1. And so now we can figure out K1. And so if we're adding these two equations, that means that K3 times K2 to the -1 equals K1, right? Just making sure we're all with this step. So back, let's just go back for a second to these notes. So we said that if we added equations that we can just multiply their equilibrium constants. And so in this case, we're adding K2, or excuse me, K3 plus the flipped of K2. So that's why I put K3 times K2 to the -1. And so now we just need to multiply these. You could also, of course, rewrite it, whatever's easier for you. So we have K3 is 1.4 times 10 to the 7th times K2 inverted, so that's 1.0 times 10 to the 5th. So you could even do some mental math. So then I think you get 1.4 times 10 to the 2nd. I'll probably plug that in my calculator just to double check. Is this what other people got? So that's what I get in my calculator too. Thumbs up, thumbs down. Okay, I see some nods. Okay. Looks like I was successful, so. Excellent. All right, questions before we continue? And so kind of the nice thing, so now if we look at this, so usually we're either working with solutions or we can also do the same thing with gases. And so we have, just note the slight differences. So we have Kc when we're talking about concentration, and again, this would probably be molarity that you would be given this expression in. But you would have, again, a similar expression for gases. It's just instead you'll be plugging in pressures into that expression. So notice it's the same thing. You raise it to the power of the coefficient. So very similar form. The only thing that you might have to do is we want to be able to interconnect Kc and Kp. So if you're given it in molarity versus your pressure. And so in calculating Kp, our partial pressures are always in atm. And so Kp and Kc are not necessarily the same because you have a difference in units. And so Kp equals Kc when your change in moles is 0. And so that makes sense, right? If you add like more moles of gas or you have less moles of gas, then they will not be the same. And so we have this relationship. So Kp is equal to our Kc constant times RT to the power of delta N. And so your change in N is the difference in the number of moles of reactants and the number of moles of products. So let's practice that. So we're given this expression. So nitrogen monoxide is a pollutant in the automobile exhaust, is oxidized to nitrogen dioxide according to this equation. So 2 equivalents of NO plus oxygen give you 2 equivalents of NO2. And so we're given the Kp, so our equilibrium constant in terms of pressure is 2.2 times 10 to the 12 at 25 degrees Celsius. So what would that be in terms of Kc? Oh, sorry. So R is our gas constant, so 0.0821. Yeah, it has to be in Kelvin, exactly. So it goes back to your R constant. So if you're using this one, then it's in Kelvin, yeah. And the gas constants usually need Kelvin anyways. So are we looking here?
So put your 2.2 times 10 to the 12 on one side of the equation.
Is equal to, so trying to find KC times, and then what's our delta N?
-1.
So -1. And this is kind of tricky. So make sure you're doing products minus reactants. This is easy to mess up. And so in this case, right, we have fewer moles, so all you do is you tally up, and so notice if you're doing this, right, make sure that they're all in the gas phase. It's kind of a trick that we haven't gotten to. But here we have gas phase, so we have 3 moles of our reactants. And then only 2 moles of product. So 2 minus 3 gives us that -1. And then, great question earlier, so with our R, so 0.0821, that means, what's our T, 298, right?
Yes.
Thank you. Really sanity check, and then to the power of -1, so all of it's to the power of -1. And so y'all can help me out. My math here. And then, so now I just need to divide, I think. Divided by this. So I get a KC of 5.38 times 10 to the 13th. I see a lot of nods. So KC times 10 to the 13. Excellent. So let's try another one, just a little practice. So for which reaction does KP equal KC? So look through them carefully, watch those states. So do we think A has the same KP as its KC? So I see some no's. What about B? Would KP equal KC with B? See some no's there. What about C? Would KP equal KC? Yeah.
Like, can they be in 2 different states? Like, can your products or reactants be different states? Or is that the giveaway?
They can be, but then you have to look at, well, who's in the gas state? So what you're really, so we might have to go back through these. because I got no's for all of them, but which one has the same moles of gases? So let's look at B again. So if we look at B, so we can ignore the solid phase, ignore the solid phase. So we're just comparing, well, this has 3 moles of gas of CO, and then we make 3 moles of gas of CO2. So we could ignore everything in the solid phase, so yes, it is B. And then if we go look at these, so we have 2 moles of gas versus 1 mole, so that doesn't work. This has no moles versus 2 moles, so that'll be different. So only B was the correct one. Yeah.
Ask another question. So if you had like a solid and then 2 different types of gas, and let's say that you had like 3 moles of CO and 2 moles of, I don't know, some other gas, and then you had 5 moles of gas on the other side.
Yeah.
Is that still
Er.
like, but like maybe a different combination of moles? That's still cool, like they don't have to be the same moles of the same gas on reactants and products. So like,
Yes. As long as they're, so if you're saying, let's say we had like 3 moles of A gas gives us 2 moles of B gas plus 1 mole of C gas, is that what you're saying? So yeah, that would work. That would be the same as long as they're the same total. But yeah, as soon as, let's just say we had 3 of A, so this would be the same, and 2 of B and 2 of C, like obviously that doesn't work now. And so this kind of leads us into our next little section here. And so the concentrations of pure solids and pure liquids do not change during the course of the reaction. And so because our concentration doesn't change, solids and liquids are not included in the equilibrium constant expression. And so that means, right, like either water, or let's say you're using a liquid reagent, then it would not be included. But of course, if you have like a solution with a concentration, then you need it. And so that brings us to this reaction. So we have CO2 plus H2O gives us H plus ions and bicarbonate. And of course, that means that we do not include this liquid. So it's just what the reaction is taking place in. So that's a large concentration. The concentration is not going to change. So it's only dependent upon our ions and then, of course, our CO2 concentration. And so we could write our expression like so. And so same thing with this sort of concept here. And so in this case, we have, looking at this decomposition reaction, so 2 equivalents of carbon monoxide gives us carbon dioxide plus carbon. And so once again, this piece of carbon solid does not really affect our equilibrium. It's limited by surface reactions anyways. And again, your concentration of carbon blob isn't changing. You just have a big mass of carbon. And so let's do a little practice. So write your expression for the equilibrium constant for this reaction here. So would my calcium carbonate be included in the expression? What about calcium oxide? All right, well that just leaves us with our CO2 then. So our Kc is equal to CO2 and no coefficient, so that's all we write. Okay, do another little practice. So try it for this one. just gonna run to the bathroom because I drank way too much water. And clearly, hour and a half is too long tonight. All right, so what do we get for our expression here?
CO2 squared all the top, and the HCl for O2 on the bottom.
Excellent. And so good job in leaving out the water. So again, our liquid reagent. So we did not need to include that. Everyone get this? Excellent. All right, so now more math part. So calculating equilibrium constants from measured equilibrium concentrations. So the most direct way of finding the equilibrium constant is, of course, to measure the amount of reactants and product in a mixture at equilibrium. And so, of course, you could do this right by maybe a spectrophotometer. That could be one way. If they were colored enough, we could, of course, make our calibration curve with our concentration dependent on molarity. Then we could monitor some reaction and then notice when it's at equilibrium, when our absorbance is not changing. And again, the equilibrium mixture may have different amounts of reactants and products, but the value of the equilibrium constant will always be the same as long as the temperature is kept constant. So this is important and useful for us. And so the value of the equilibrium constant is independent of the initial amounts of reactants and products. So this also helps us. So whatever the equilibrium constant is for the reaction, we can use that. And so with stoichiometry, we can use it to determine the equilibrium concentrations of all our reactants and products if we know some initial concentrations and one equilibrium expression. And so we'll use the change in concentration of our material that we're monitoring to kind of determine the change in the other chemicals. So this could be useful. So again, thinking back to the spectrophotometer, maybe we can only measure one of those, either reactants or product, with our spectrophotometer and using the concentration. So here's how we approach this. So we have the following reaction. So carbon monoxide plus 2 equivalents of hydrogen gives us methanol. And so it says we have a reaction mixture at 780 degrees Celsius. It initially contains a 0.5 molarity concentration of CO and a 1 molarity concentration of H2. So at equilibrium, the CO concentration is 0.1 molarity. So find the equilibrium constant. And so the way to approach these is setting up this little ICE table, or I like to call them RICE tables. I'm sure you've heard either term interchangeably. So RICE, I just like it so you can write the reaction. So I'm just going to rewrite our reaction. So CO plus hydrogen gives us methanol. And then our I in our RICE table, or ICE table, stands for initial concentration. And so we go back. So it gave us the initial concentrations. So that was 0.5 molarity and 1 molarity. And then, of course, we're assuming if we're starting off, right, nothing has happened. So that means our initial concentration of product should be 0. And so in this blurb here, it said something about we're going to use stoichiometry. And so that's where that comes into play. So if we're looking at our change then, so we have 1 equivalence of CO and 2 equivalents of H2. And so that means that for every equivalent of CO, so that's minus X, then we're consuming 2X of H2. And then again, going back to stoichiometry, so that gives us 1 equivalent of methanol. So that's going to increase by X. And then let's get our equilibrium. And so they didn't give us everything. They just told us, well, at equilibrium, maybe they could only measure CO. Maybe they were monitoring this by like carbon-13 NMR. That could be appropriate. And so it's determined that the equilibrium concentration of carbon monoxide is 0.15. And so now we need to do some math here. And so notice, so again, we have this minus X, minus 2X, plus X. So can we solve for X then from this information? -1 or? So you're looking, like, so let's just say let's look at CO for a second. So it started at 0.5 molarity. It went by a change in X, and then we ended up with 0.15. So we could probably subtract, right, 0.1 minus 0.15 to give us X. So let's start with that. So that means X is 0.35. And so if X is 0.35, now we can solve our equilibrium concentrations based off of the CO data. And so now we can say, well, H2, we started at 1 molar. It's minus 2X. So 1 molarity minus 2 times 0.35. So that means our equilibrium concentration for H2 would be 0.3 molarity. And then our final concentration of methanol, so we started at 0. It just went up by X. We found X, so this is 0.35 molarity. And so now we have all our equilibrium values. So now we can plug them into our expression. So let's first write our expression out. That means my equilibrium constant is going to be equal to my methanol concentration over H2 squared times CO. So this is just from before. We know how to write our expression. And now that we have our expression, all we have to do is plug these values in. And so now just taking these values, so 0.35, I'm just writing it out first, so 0.3 squared times 0.15. And so now we just have to punch it in and just watch for order of operations. So I get a KC of 25 for the equilibrium value. So I see at least one nod, some more nods. Any questions about this one? All right, let's do another practice. So same reaction that we just did. And let's say it's carried out at a different temperature with a different initial concentration. So this time starting with 0.27 molarity and 0.49 molarity for H2. And it says at equilibrium, our concentration of methanol is 0.11 molarity. So how would you approach that? So did we at least get to hear kind of like the initial setup? And then what's the little key component here that we need? Yeah,
We already know our x value because we're starting at 0 and ending up with 0.11.
excellent. So now we have x. So x is 0.11. Now that we know x, we can just solve for the rest of these values. So what do we get? 0.16 for CO. And what's 0.49 minus 22, 0.27. Does that look right for those values? And so now we can plug it into this same expression, so same equation, same expression. I'll just rewrite it really quickly. And then what do we get for this value? Again, watch your order of operations here. So I get 9.43. I see some nods, several nods. Excellent. So now looking at the next section, so we'll probably have to continue this on Tuesday, but we'll see how far we get. So now Q is really just a formality, and it's just like a snapshot, is how I think of it. So basically, we're looking at our reaction mixture, but when we have the value of Q, it's essentially telling us, well, we're not at equilibrium. Let's just say we could, take a snapshot of our concentrations at any point in time, and then plugging them into this expression will give us Q. So I'm trying to give like the quick rundown of Q. So again, notice, right, Q has the same setup as K, because it's, again, like a snapshot of K. So I'll write that again. This is our snapshot of K. So again, K is at your equilibrium, Q is at any point. And the whole point is you're comparing Q to K and then figuring out, well, which way is my reaction going to go? And so blah. So I'm skipping the words. So let's look at the graph better, because the graph, I think, explains things a little better. And so we're just looking at this generic reaction here of A to B. And so our reaction going A to B here. And so we're given our equilibrium constant value. So that's just graphed here. And of course, that's always just our constant. And so now this is saying, well, let's take a snapshot of our reaction. Let's just look at this point in time. And so if we were to look at our Q at this point in time, so Q is going to be less than K. And so we can just think about that. So again, K products over reactants. So if Q is less than K, that probably means we're not done forming products, right? It needs to continue going till we get to K. And so that's what this graph is showing. So we just keep going, keep going. Now that's our equilibrium value. So of course, our reaction is at equilibrium. Forward rate and reverse rate are the same. Now if we were to look at the snapshot at this point in time, so again, products over reactants. If Q is greater than K, though, that probably means we have too many products. And it's going to go in the reverse direction. And so that's all that's shown here. So again, Q greater than K, we're past our equilibrium or something, or maybe we started past it, and so now the reaction is going to run backwards until we get back to K. So let's do this one little practice. I'll probably have to call it a day. All right, so we're looking at this reaction mixture. So iodine plus chlorine gives us iota chloride, and we're given our Kp expression. And so our reaction mixture, and it's giving us our numbers in ATM, so that's good. We don't have to think about KP to KC conversions. And so it's giving us our pressure is 0.114 ATM. For chlorine, it's 0.102 ATM. And our product is 0.355 ATM. And so it wants to know, is our reaction mixture is it at equilibrium, and which direction will it proceed in? So I'll just write it out for the interest of time. So just set up your expression first. And remember, KP should look just like KC essentially. So similar form. And so now we can plug in our values and then compare them. So over my reactant concentrations. And let's see what we get. So 0.355 squared, divide, don't forget your parentheses. And so do you get a Q of 10.8? So our Q is 10.8. And again, just think simply, so products over reactants. So now we can compare our K. So let's just start with, is our reaction mixture at equilibrium? So I see a lot of shaking heads, so no. And then which direction will it proceed in?
Continue proceeding in the product direction.
So in the product, so that means in the forward direction. And so excellent. So again, you're just comparing our KP is all the way at 81. And again, that's just our ratio, thinking simply of products to reactants. And so we're under that, so no, it's going to go in the forward direction to make more products. All right, I think we'll have to stop there, unfortunately. So looking ahead, we'll have to continue with the math on Tuesday, so I'm just kind of giving you an overview. So it's going to be kind of more ICE tables and equilibrium. Plus, we need to go over the math and how to do these. Yeah, the Le Chatelier's principle shouldn't be too difficult. You could probably read that on your own, but we'll go over the math, and we'll go over Le Chatelier's principle. So yeah, we'll have to pick this up on Tuesday, and I think that should lead us into the next chapter, because like I mentioned, we're doing a lot of equilibrium, so it should look like a lot of the same stuff, hopefully. So we'll take our 10-minute break, and then we'll do the quizzes. And then I'm also thinking, so next week we'll do, of course, the Chapter 19 quiz, but then that leaves us with I forget what chapters are last week, but maybe we'll do like a take-home chapter quiz or something, bonus, extra, to help you practice for your final. All right, break time, and I'll do quiz time.
What are, the plans for lab today since?
We'll still have our regular Thursday lab, and then the Tuesday lab people will make it up next week. And if you are Tuesday and you want to come in today, you can.
I'm sorry, I was a little bit late. I had an emergency dental appointment this morning.
Oh, no, that's not never fun. Ah, Jared.
Yeah.
I got your exams chilling here. Handed it back.
Good news is that there was nothing wrong, so.
You just have pain or?
Yeah, my mouth's bleeding a lot and
Oh, no.
pain, but it's.
Did you have a question, Jared?
Yeah, I can email you, but I just needed, chapter 17.
Oh, the homework?
Yeah.
Hang on. Ask that. Did you need to take the
always just-
17 quiz?
I did. Was there a 16 quiz too?
Yeah, I could give them to you now or send them to the testing center.
Yeah, I'll do it in the testing.
Okay.
Only 'cause I forgot.
Oh, yeah.
I did print off 17, right?
Yeah, I have 17 printed, so I can send that over. Oh, I'm looking for the homework too for you. Oh, here it is. Do you need a chapter 17 homework?
Yeah, thank you so much.
And I'll send quiz 17 and 16 to the testing center.
I was looking at my grades on Blackboard, and it said that I didn't turn this in.
Oh.
I just wanted to make sure.
Oh,
that you
weird.
got it.
Because it was graded.
Yeah.
That's annoying. That is weird. I don't know
No worries.
how that happens. Well, I don't put a grade on it until it's inputted, so it's like irritating to me.
Yeah.
That's why y'all gotta check.
What time is lab again?
2:30.
I'm gonna go work in the trio lab for a bit and brain break because my brain's gonna explode.
Okay, I want a pile of stuff from you though.
Start. Finishing my labs. I was so proud of myself yesterday. I got 8 hours of studying in.
Nice.
Most of that was taken from my engineering orientation class. I'm kind of burnt out by class. It wants us to do like really complex calculations, like physics, and like sometimes I have to do linear algebra problems in Excel, and I'm in math
Oh,
95.
man.
Also, I'm not going to be able to take, in Gen Chem 3 next term because, it conflicts with my pre-calc class and, since I really need to be able to start taking calculus and, the physics-based calculus series in fall next year, I need to prioritize.
So you'll take third quarter next year?
Yes,
And so what-
probably in succession with first quarter. I don't know how I'm going to figure it out, but I might take it completely out of order.
Take what out of
Oh,
order?
chemistry, the chemistry quarters.
I'm not following.
So my Math 111, the only in-person Math 111 is at 11 a.m. and starts at 11:30. To not derail my calculus, starting calculus in the fall. I have to take 111 in the spring. Does that make sense?
Yeah, it's just so irritating that the classes keep conflicting.
Yeah. I would like to take chemistry because I feel like I would do better if I took it in succession.
Yeah, because we're just kind of continuing on.
Yeah.
Although 111 is also offered online, I just don't know that you'd want to do that.
Just because of how my brain works, and I specifically cannot take online classes because I just forget they exist, and then I tend to do poorly, even though I have all the potential to do really well in the class, just because I can't keep schedules straight if I'm not in the classroom.
Yeah, because there's also a 9 a.m. session, but I guess it's by Zoom only. But I think Kevin's 11 a.m. is a hybrid anyways. Because I see Kevin Murphy teaching Zoom 11 a.m.
Oh, you know, it's people can join via Zoom, but classes in person every day if you want to.
Yeah. I don't know. If you really wanted, you could make it work. Because otherwise, you push Chem off a whole year,
This is true.
which is not great either.
Would it? How much do you think it would hurt me to come into lecture 20 minutes late every day?
To this lecture?
Yeah. So if I were to go straight from,
Oh, yeah, that wouldn't, I feel like it wouldn't be horrible as long as you know, watch, because you go watch the lectures later.
This is true. Yeah.
I'm not sure, because you have to think, we can talk more too. All right, I'm going to hand out the quiz as usual. Give me your muddiest point. I would have your rate law cheat sheet again, and if anyone needs a cheat sheet, I can try to print some or find them. Don't think you need calculator. And then don't forget to turn in everything. Many of you are missing many assignments, little things, homeworks. Get those in, labs. Oh yeah, I found. Anyone need rate law cheat sheets for today? Probably gonna want them for your units. Oh my goodness. See. 1, 2, and y'all, I think I have more. Just close the page. Anybody else? Oh, one more. And then again, check your grades. Don't forget to check your grades. I've already found a few errors where homework didn't get saved in midterms, so just check everything. Yeah, you can put homework in one file and labs in the other. Oh no, paper cut?
Yeah.
Yeah, we can do makeup labs too next week, probably on Thursday. So if you need a makeup lab, just send me an email.
Trying to figure out what this day or on Tuesday for this week's.
Yeah,
Let's see what Jacob wants to do.
okay, yeah, sounds good. And then, yeah, makeup probably on Thursday of
Okay.
next week.
You think I could, would I still be able to make up that lab I mixed the one book for the kinetics one? Or do you still want me to do that online?
Which one, remind me which one that, is it the distillation one?
No, I did the distillation one. I think it was the one after.
Oh, the acid-base titration?
Pretty sure I did that one. Yes, I did that one. My computer just decided. Oh. I'll figure it out, but since we'll have all of next week. I think it was when you said that, it's probably a good idea to do it online because, the solutions have to be fresh
The iodine one,
I
yeah,
think it was that one.
yeah, that one might be harder to make up. Unless you really want to do it in person, but I would have to talk to the stock room, because I think they'd have to make new solutions.
If you can just use, is the, information, like data already on the Blackboard for that?
Yeah,
I can just, extrapolate from that data. I'm gonna go print something.
You owe me a bunch of homework, don't you?
Yeah, I
Have
do.
you been at least kind of doing them along the road, or?
I've been trying, but they're all like half done, so I just need to get the other half done.
Yeah, do it, do it. And then, do you have the rate log cheat sheet thing? You'll probably want that for today's quiz. If you don't have one, I can probably find another.
I can. Is it just on Blackboard?
It's like in the notes. And then homework's there. Here, I got one. Oh, shit. Just took down my computer.
You want me to just put it with the other quizzes?
Oh, yeah.
And then you said that next Thursday is the makeup labs?
Yeah, for like everything else. So regular lab today, I don't remember what section you're in.
Yeah, I'm in today's section.
Okay, yeah. So then we'll do our last lab, and then if you need to make up anything next Thursday.
Next Thursday.
And then just send me an email so I know.
Okay, and then are we doing the checkout next Thursday too?
Yeah,
Okay, I'll just do it at the same time.
yeah.
Thank you.
Yeah, I forgot to take an extra quiz of last week's quiz, so I just looked at you and used, and I used both of you. Oh, yeah.
My zone most of the grade, I was like,
Yes, I do. I was so confident about that one.
I know, usually people do really well in the labs though, slash, as long as you write something about what happened, but yeah. And nag is no answer given.
oh, okay.
Yeah, I do that just so you don't come in and fill it later and be like, why'd you mark me off? See, it's done.
Perfect answers though. Chapter 18. It's just last week.
People need to do their reading questions too.
Pretty close to me. I only have a few more.
Oh.
I'm just trying to figure out how to do
Oh.
that.
So all that's saying is it's trying to convert it to milliliters, and so if you assume,
22 drops per milliliters.
yeah,
So it's
you-
just adding the drops that we put in.
or divide, yeah, so you have, if you use this,
Mhm.
then you just do like 1 divided by 22, 2 divided by 22.
Okay.
So it's like really small difference.
Okay.
This is like my least favorite part of the quarter, is trying to enter grades, finalize grades.
somebody working?
I'm
Is that your
just
stuff?
finishing up,
Oh, okay.
yeah.
Well, beautiful drawing. Yeah. Three colors.
not, yeah, no, actually I cannot log her out, it's her laptop. Ah. Well, otherwise we start. Pedestrian, right? Done this for years, I still can do that. So everybody got the handout I handed out last time, right?
Yes.
Yeah, okay, good. I'll just parked myself in between before the chemist cleans up there.
Sorry. This copier took way too long.
Yeah, that copy has an outage for sure.
Pay for it, it's like $3 for
I know.
$2.
I want to do that.
All right. Chemistry's gone. I take my stuff away, I just have to park myself somewhere. There's still stuff here. What is this? A cheese stick and.
She said she couldn't,
Oh,
she
she said.
couldn't get it all at once. She said she.
Oh, she's going to come back, okay.
Yeah.
Thanks for the snack, but,
I think like you're advised to eat random cheese sticks.
yeah, no, trust me, I'm too finicky for that. People who Lysol their desks do not eat random cheese.